Hello everyone, and welcome to this video on the functional derivative, part 2. Now this video looks at how to find the functional derivative of the metric and inverse metric tensors with respect to each other. It involves the use of the Kronecker delta, Dirac delta function, and tensor index manipulations. So in particular, we're going to be looking at this particular variation. It's the variation of the inverse metric with respect to the small changes in the metric, and the variation of the metric with respect to small changes in the inverse metric. And we'll also have a look at, finally, a third case as well. So let's make a start. And am I going to be in the way here? Maybe I can hide that for a bit. All right, now, the inverse metric tensor satisfies the following relationship with the metric tensor. So we have G alpha mu contravariant, 2,0, rank 2,0 tensor, and the metric G mu beta, which is 0, 2 tensor. And that's equal to the Kronecker delta here, alpha beta. Just notice too, when we're summing, when alpha and beta are equal to each other, when we're summing the Kronecker delta, we have a 1, and we have n lots of 1, up to n dimensions. So just remember that. It's not just solely equal to 1 only. All right, so now to find the functional derivative, that's the variation of the inverse metric with respect to small changes in the metric itself, we consider the variation of both sides of the equation. So we take this equation here and we vary both sides. We look at the variation of both sides, the delta of both sides. Now, the right-hand side is 0 because the Kronecker delta is a constant, and so the variation of the constant is 0. So that bit's 0. On the left-hand side, though, we apply the product rule for variations, and delta of that product is delta of the inverse metric times the metric plus the inverse metric times the variation of the metric. Right, since the variation of the Kronecker delta is 0, that means that all of that is equal to 0. All right, now what we want to do first off is we want to isolate this term here, or this part of the term, this element of the term. So first we're going to move this bit over to the other side, so we'll take that over there, hence the minus sign here. And then what we're going to do is to isolate the variation of the inverse metric. We're going to multiply both sides by this inverse metric in order to use the Kronecker delta on this, so that we can produce this term by itself. So when we do that, we're multiplying on the right here by G inverse beta mu, or upper indices beta nu, the inverse metric. And notice there's a beta here, there's a beta here. The Kronecker delta will apply between the metric and the inverse metric. The product of those is the Kronecker delta. And that's equal, and then on the right-hand side must do the same there. So we multiply by that G beta nu on the right. And in doing that, this simplifies then too, so just repeating this line here. And what we're going to do is we apply the Kronecker delta here on these two elements. So that's delta nu mu. Notice see we're summing over the beta there. We're left with nu and mu. Okay. And so that gives the Kronecker delta there. And we get over here, this remains unchanged on the right, and will continue down here also unchanged. But notice here, the variation of the inverse metric times the Kronecker delta means that with one index mu up and one index mu down, we're going to sum over those and they sum out, and then we're left with a nu. This nu here goes here, so we're left with the variation of G alpha nu instead of G alpha mu. Right-hand side hasn't changed. Okay, so we'll use this expression, and later on too, we'll come back to this particular result here, and we'll be using that for that third result I've mentioned earlier. All right, so let's move on. All right, so we have, just repeating the last line again, the variation of G alpha nu is this. Okay, what I can do now is divide both sides by the variation G mu beta. So now we have the variation of the inverse metric with respect to small changes in the metric itself is equal to the product of the inverse metric with itself, and the minus out front. Now, this tells us how sensitive the inverse metric G alpha nu is to small changes in the metric G mu beta. I should point out, as I will when I finish this video, that we're talking about this variation, this functional derivative here at a point. Just like with the ordinary derivative, when you find the ordinary derivative of a function, you are finding the rate of change at a point. Yes, in practice, we produce derivatives all the time, calculate them all the time, and it gives us another function which tells us how the original function changes, but again, at each point. It's a the derivative is a general expression which tells us how that function changes once we substitute in for a particular point. Same here with the functional derivative. This is occurring at a point. It will give us the variation at a point, the variation in the inverse metric with respect to the metric at some point. I'll tidy that up later. For the moment, though, let's just concentrate on indices and what the functional derivative is. So, okay, so there's its intuitive sense what it's about. Let's go back to the equation now here. So that's our first functional derivative. And now what I want to have a look at is another one where we have the metric on top and the inverse metric down below. So we'll have a look at that. So let's go back to the original equation. That was varying both sides of the product of the inverse metric with the metric. Remember the right-hand side was 0 there because the variation of the Kronecker delta is 0. Okay, so let's have a look here. We're going to, this time now, we're going to get this second term here on the left, and we're going to move the right-hand side over. So let's do that. We get a minus here. Then what we're going to do is on the left, we're going to multiply by G nu alpha. Notice there's an alpha here and an alpha here. And so we'll see the Kronecker delta will apply. And then on the left-hand side here, we'll also multiply too by the G nu alpha. All right, when we do that, the Kronecker delta applies here. We're summing out over alpha. We're left with mu and nu. So the Kronecker delta applies mu there. All right, and then what we're going to do is here, we're going to have minus G alpha, G nu alpha is delta G alpha mu, G mu beta. All right, and so the variation of, now notice here, we have a mu up and a mu down. And when mu is equal to nu, okay, we then results here, and we go from the variation of G mu beta to the variation of G nu beta. That's the work of the Kronecker delta doing that. Right-hand side, unchanged, of course. All right. Now, so on the left-hand side, we have the variation of the metric, and is equal to the product of these elements here. So dividing through by the variation of the inverse metric, we have the variation of the metric with respect to small changes in the inverse metric is equal to minus the product of these, of the metric with itself. So this, okay, the variation of the metric with respect to small changes in the inverse metric is this, and the variation of the inverse metric with respect to small changes in the metric is this. Notice these are the product of inverse metric, and this is the product of the metric. Okay, again, this is all happening at a point which I'll tidy up shortly. All right, so how about the variation of the metric with respect to small changes in the metric? What does that give us? All right, well, from earlier, we had this result, remember? And what we're going to do is we're going to be, I'll tell you in advance now, is we're going to need to use this term here to put that underneath there. So what we want to do is we want to vary, change some indices here. So what we're going to do is I'm going to, where the beta is, I'm going to change that to gamma. And we can do that because when you've got one index down, one index up, you're summing that out. You're free to change those. It's just the free indices which are not to change because they have to equate on both sides. So on the left here, we've got an alpha. So somewhere over here, we must have an alpha. On the left here, we've got a nu. So somewhere over here, we must have a nu. So there's a single nu here. There must be a single nu here. There's a single alpha here. There must be a single alpha here. Otherwise, the equation's not correct. Okay, so I'm free to change pairs where you're summing indices, one up, one down, they sum out. You're free to name them however you like. So I'll replace the beta with gamma. I'll replace both of the mu's there with epsilon. All right, and so the variation of G alpha mu, because I'm going to replace mu with mu. So that mu there will be mu. And then I'm going to have the variation of the inverse metric alpha mu is minus this product here. All right, so let's see. We've got from earlier the variation of the metric with respect to the inverse metric is this here. All right, it's the product of the metric with itself and the minus out front, of course. And what we're going to do now, in order to find the variation of the metric with respect to small changes in the metric, is we need to remove this inverse metric. So we're going to resort to this relationship here. And hopefully now you can see why I've changed the indices. So keep the numerator. So the denominator here, delta G alpha mu, we're going to replace that with all of this. So it'll go in here like that. All right. And over the right here, we still have this. Okay. Now what we're going to do is multiply both sides by these inverse metric elements here. All right. So they appear on the right-hand side now, and they're gone from the left. So that the minus and the minus cancel. G alpha epsilon will go up to G nu alpha, like this. You can see there's an alpha there, an alpha there. The Kronecker delta will apply. Here you've got G mu beta, and over here you have G gamma mu. So they'll go over here, and you'll see there's a mu down here and a mu up here, and you'll be able to apply the Kronecker delta there. So, which is what we do. So here we have Kronecker delta epsilon nu, because there's a single epsilon and a single nu. All right, and here there's a single gamma, single beta, so that applies here. So this, the variation of the metric with respect to small changes in the metric, is this product of Kronecker deltas, but we're not quite finished yet. Okay, so let's move on. All right, now, maybe I can go up here. Maybe not. All right, so now we have the variation of the metric at some point on the manifold X with respect to small changes in the metric at some point Y, okay, is equal to the Kronecker delta we found earlier and the Dirac delta function, because we're talking about a point. X and Y must be the same point. We're not comparing changes at different points. Just like with the derivative of an ordinary function, you are finding the rate of change at a point. You're not finding some rate of change at different points, at two different points. That's not how the derivative works. That just doesn't make sense. To indicate that we're talking about one point, the Dirac delta function comes in here. Okay, when x equals y, this is 1. When x doesn't equal y, it's 0. Okay, so the functional derivative, I'll put that back now. So the functional derivative, this measures how the metric tensor G nu beta at a point x changes with respect to an infinitesimal change in the metric tensor G epsilon gamma at a point y. In the context of continuous fields, this derivative is analogous to a Dirac delta function, which ensures locality. Okay, so again, x and y are the same point. So for a given metric tensor G nu beta, the functional derivative with respect to itself is given by this. Okay, the Dirac delta enforces locality and enforces this occurs at a single point. So where the delta x minus y is a Dirac delta function, ensuring that the variation is localized at the same point. Okay, so we're talking about the same point on a manifold, and that's important, and that's where the Dirac delta function appears in there to make that clear. It is localized to the same point. Just as we do with ordinary derivatives. All right, now, so let's see, I think almost there. Okay, and I'll bring this down here out of the way. All right, so the functional derivative of the metric tensor with respect to itself is, so the variation of the metric tensor with respect to small changes in the metric tensor is this object here, the Dirac delta function enforcing locality that it occurs at the same point. So this result tells us that the variation of the metric tensor G nu beta with respect to itself is only non-zero when the indices match and the points in space or space-time coincide, which is precisely captured by the Dirac delta function in both the indices and the coordinates. Indices in the Kronecker delta, and the Dirac delta enforces the same location. All right. So finally, our two results from earlier, and this time point x, point y, and with the Dirac delta function to ensure we're talking about the same point in the end. Okay, so the variation of the inverse metric with respect to small changes in the metric is this, and the variation of the metric with respect to small changes in the inverse metric is this. All right, and I think that is it. We're finished. There wasn't another page. No, there wasn't. It's done.